Hello, everyone. I'm really glad to be here at Hacktivity again. This is my fourth time. My name is Domonkos Tomcsanyi, or just Domi Tomcsanyi. And I've been working with Wi-Fi and 3G and other radio-related stuff since 2006. And today I would like to present to you the current state of GSM and how it's secure or if it's unsecure. But also would like to give you a lot of tools, and also we'd like to give you a complete walkthrough of sniffing GSM, and after sniffing it, cracking the key, and then after that, listening to the conversation that has been broadcasted on the air. So, and I would like to encourage you with that to go home and try it for yourself too, because as you will see, my theory about GSM is that it's so much broken and it's so insecure that people need to get their hands dirty on it and they need to experience it. And then maybe we can push a little bit on the mobile network carriers to fix the flaws. But before we are getting into the goodies, I would like to give a moment of silence to a man who has really been contributing to the hacking community till his recent death. This is Barnaby Jack. Many of you might have heard of him. I had the chance to see him presenting in 2011 at Hacker Halted. And I really think that he influenced so much the hacker community that we really need to think about him and remember him and never forget what he has done for the community at all. Okay, so let's talk about GSM. Like, what's the history of GSM hacking? What do we know about? Well, GSM was released in 1991 as a standard for a global system for mobile communications. And it was a standard which many carriers actually started to use. And it's right now, I would say it's the most well-known and the most well-populated, most popular network for mobile phones. And just 3 years after the standard was released, there was the first attack paper by Ross Anderson, who had some theory about how to crack a GSM key. The GSM cipher wasn't really known back then, but some details were actually known about it, like how long is the key and how many rotations the encryption function does. So Ross Anderson made a paper about that and said that in theory GSM could be hacked in like 2 on the 40th power. And then actually many papers followed along, and the theory was quite ahead. So in 2003 there was actually reasonable theory saying that how A51, the cipher used in GSM, is applied in the GSM system. It could be broken, and what would be the requirements for that. But so theory was ahead, but there was nothing in the practice, because to get GSM data, you would need to have some kind of sniffer for that, and you cannot just go to the shops and buy one sniffer for GSM. At least you couldn't do it like 10 years ago, let's say, because it was only for government users and also for mobile carriers for some testing stuff. So there was nothing really available for people. So then Carsten Knoll came along. His name must really need to be mentioned because he was the one who carried out this project and teamed up with many people. And this German gentleman was able to actually successfully carry out all the steps needed to have full GSM sniffing and cracking. So what's the timeline here? In 2009, he released rainbow tables for the A51 cipher. And these are around 2 terabytes of size. And these rainbow tables could be used to crack A51 keys. And then after that, he needed a sniffer device. So naturally, he turned to one of the well-known sniffing device or radio device in the open source community. That's the USRP, which is a software-defined radio. And then used that and created some code with coworkers and his whole team to be able to capture data and then use the rainbow tables to decrypt the data. And then in 2011, he started to use the Osmocom BB project, which is a quite new open source project, and it aims to create an open source firmware for such old Motorola phones. And how they did it, they actually reverse engineered the baseband and how the baseband works and created open source software for it. So right now, you can use such a phone with open source software and control everything like on the baseband level. So it's a much deeper level of control than you had on any other phone, because you are controlling everything that is going on the phone. So using this project, he was able to actually capture data from hopping channels, which meant the reason why he did this was that the GSMA, who is the organization behind GSM and 3G, said that, okay, you can capture data with the USRP, but the problem is that many operators use so-called hopping channels, which means that after the call is connected, the phone will hop along some frequencies and follow those frequencies of the certain operator or carrier. But the USRP wasn't able to carry on with this hopping motion. So the GSMA said your attack is not so practical. So he came up with the solution 1 year later that using a real phone, which has the hardware actually built for even capable of hopping, use that hardware and be capable of hopping along with the conversation. And then he presented the attack at the CCC conference, showing a full GSM sniffing attack. And of course, there is the last one, which just happened this summer, the SIM card attack, which I think many of you heard about. He was actually able to run own code on SIM cards, so pretty much owning the device from remote with some SMS messages and running code on the SIM card. Okay, so let's say you are all about GSM, you would like to get into it, you would like to experience it, how it works. And why hasn't many people done so far? As you have seen, there has been quite a progress in the open source community. It seems to be that tools might be available, so why not many people are doing it? Well, it is hard because there is not many easy starting points. There is nothing like going out to, let's say, YouTube. Like when you're trying to do Wi-Fi hacking and you are like a script kiddie, and then you would like to know how to do it, you go to YouTube, type in like how to hack Wi-Fi and watch some videos and then maybe start reading about it and then figure out how it works. And you also have the hardware at home to try it out for yourself. But in case of GSM, there is not much of information out there. Much of the information is mostly for professionals, so without any prior knowledge, it's quite hard to get into it. And then getting a proper hardware for the whole stuff, it's also not that easy. So right now, if you would like to go to the open source option, so not going to the commercial governmental options, which is like $100,000 or something like that, you can either use the USRP or use the Osmocom BB. The USRP is really expensive for a hobbyist. It's around $1,000 or $1,500 for one unit, and you also need to buy some additional cards in it for reception and also for transmission. So it's not that easy to get it in, and it's quite expensive. Osmocom BB, however, is actually quite cheap because these phones are really just like old dumb phones from 2007 or so. So these could actually be bought for, I don't know, 15 or 20 euros on eBay. But there is no code for it. And the Osmocom BB project that's actually having the full baseband firmware in it, it's really hard to like understand and see like how it connects together and which parts is doing what. So you pretty much end up like between two chairs sitting on the floor, because either you need to pay a lot of money or either you need to understand a quite complicated code. And to support this statement which I made about Osmocom BB, I would like to just put out the last point I wrote on the PowerPoint. This is like, I actually found 3 theses of MSc students on universities which said in the abstract, all right, we're going to do some work with Osmocom BB, maybe even do the same with what Karsten and Sylvain did at CCC. So we will actually recreate the whole GSM sniffing attack. And then in the end, they all said, well, we failed miserably because it was impossible to get Osmocom BB up and running in the time frame we had, or it was even impossible to read through the standards needed to understand the whole code in the time frame which was given for this thesis. So it's quite hard. So right now, the landscape looks like this. Either you do the USRP approach, you will get code, but the cost of the hardware will be high, or you do the Osmocom BB approach, when you will not have code, so you need to you need to write your own code, but the cost of the hardware will be much lower. So to solve this problem, what do we need to do? Well, this is what I would like to have. as a hobbyist getting into GSM. I would like to get something that works. That means we have code available for it. I wouldn't say it's like next finish install and then it's all up and running, but I would say it should be definitely a lot easier than getting Osmocom BB up and running or getting a USRP from the market. And also we need to have, as welcome at a USRP, something that's affordable for the people, so anyone who would like to start research on GSM should have access to tools for a cheap price. And we would also like to have something that's relatively easy to install and start with, so there is documentation or tutorials or something you can start with. And we would still like to comply with the rules of responsible disclosure, meaning that we just cannot give away like GSM sniffers for anyone, because that wouldn't be responsible. So we need to have some limitations in the code, but we still need to get the word out and get the hardware out to the people. So what's the solution? Well, RTL SDR is our solution. Anybody knows RTL SDR? Hands up. Okay, some people have heard of it. That's great. So what is it actually? Well, it's a cheap Chinese DVB-T receiver, so digital TV receiver, which are using a Realtek chipset. And some guy on the internet actually found out that it is possible to set the chip to a so-called debug mode. And in this mode, it's actually going to act like a simple antenna plus an analog digital converter. So it's going to output samples in the rate which I put on the PowerPoint through the USB port, making it possible for you to actually tune it to any kind of frequency, and then getting the bits into your computer, you would be able to do any kind of radio. It's a software-defined radio, meaning that you get samples from the air, but all the post-processing and the signal analyzing and sampling will be done on the computer. Meaning that using the same stick, which I have right here, and here is the antenna for it, using the same cheap stick, you can either listen to FM radio, you can watch TV, you can listen to GSM going on, or you can even do other stuff which is quite interesting, like listening to airplane communication. And some people actually created software which you can use together with the stick to map airplanes on a map and show like where they are, what's their speed, and stuff like that. So it's a poor man's SDR, but it's quite powerful. And as you can see, the range of the frequency it can handle is quite large for such a small device with cheap hardware in it. So the million-dollar question, of course, arises: is it compatible with the code that was released for the USRP in 2010? And the good answer for that is yes. So let's be happy about that. So did we achieve our goal with that? Well, we have cheap hardware. These dongles go on eBay for $15, literally, with shipping. So the cheap hardware is given. What else do we need? We need code. Well, I said the code for USRP was actually released, so you can use the same code together with these sticks and do the same GSM analysis, which Karsten Knoll was able to do back in 2010. And we have limitations in it, which are bad, but also good in some way, because there's just enough limitations there, so it's safe to be released for the public, but it's still fun to play with. So it's just on the margin of the compromise of like not giving away everything, but giving away so much that people would be feeling encouraged and feel fun playing with it. So what are our limitations? Well, we can only capture downlink channels because the code that's actually sampling the signals that are coming from the RTL SDR is only written for downlink parsing. So that means, downlink means that only the communication that goes from the tower to the mobile device and not the other way. So, but some smart people might think about like, if we have two mobile devices communicating, then from one uplink, there's going to be the other one's downlink. So actually, you can, using two sticks, you can actually listen to both downlinks and you will have a full phone conversation, but that's a special case, naturally. We can only do a non-hopping cell, because naturally the USRP wasn't able to hop along. These older, these cheaper models cannot hop along either. So, but the good news is that as far as I have tested, 2 of the 3 operators in Hungary using non-hopping channels on their cells. So that's something to think about. Anyone here from one of the operators in Hungary? Okay, yeah, don't be scared. And one more limitation, that the radio needs some calibration, which which isn't that hard because there is a program for that, but it's just good to know that since it's a cheap dongle, the frequency counter in it and the crystal in it is not that really precise. So to tune it exactly to the GSM channels, it needs to be calibrated, and sometimes it just stops interpreting data. So there are some hiccups in the log. But I will show you that even with such inaccuracy, I was capable of doing both SMS sniffing, which shouldn't be so hard because SMS is just like one packet in the air, as we will see. It's not called packet, but whatever. So it's just one data burst in the air. But I actually was able to capture a full phone call, and that's actually more bursts in the air, a continuous flow. So that actually shows that this SIG actually has the potential that is needed to get into GSM. So a little bit about GSM. How many of you know how GSM works, or have some ideas about how GSM might work? Okay, that's quite full. That's nice. Okay, good. So I don't need to go really into the details, but I will try to explain some of it. This is the must-have image, which needs to be in every single GSM presentation, I guess. It's from Wikipedia, and it shows the system. So you can see here on the left, there is the mobile device that it has the SIM card in it, and it is communicating with the BTS, which is actually a cell tower, and more BTSs are connected together with the base station controller, and the base station controller is managing these towers. And then, of course, there is a whole backend for it, which has databases in it and also connections to the normal telephone lines. So it has a database of naturally the customers, the currently used keys, the currently used temporary IDs of the customers, and also connections to either the internet or also to landline normal phone, which is PSTN, so public switch telephone network. But we are only interested in about the part that's between the mobile device and the tower. So we will see how that works, but we need to get some terminology here done. So ARFCN, that's the absolute radio frequency channel number, which is just get prepared that GSM has a lot of 3 or 4 word shortenings. So get ready to have a really huge amount of these, but I will try to explain most of them. So this ARFCN is actually just the frequency of the cell. So they have given it a number, and that number will specify the exact frequency. Paging means that the base station or the tower is actually paging the mobile equipment, meaning that if there is anything when the mobile equipment needs to talk to the tower will page that specific mobile equipment. And if we look at the PC word, this looks like an ARP request because it's broadcasted to everyone, and then the certain mobile device that has the temporary ID in the paging that will respond to that paging. And the whole GSM is based on TDMA, so time division multiple access, meaning that there are time slots and and many logical channels, and these logical channels are actually transmitted at certain times. So instead of other kind of division of data, there is always based on times. And then naturally between 2 time slots, there is some signaling data to say that, okay, we are over with time slot 1, now it's going to be time slot 2, and these are all divided in time. And the burst is data which is transmitted during 1 time slot, and that's 148 bits of usable data. So this is how a TDMA frame looks like. So you can see that the different time slots are in it. And then in each time slot, there is actually some more data. Like the data is divided in two parts, 57 bits each. And then between them is also some signaling data to actually be able to differentiate between the different the logical channels and also differentiate between the different data bits. And as you can see on the left arrow, the upper one is the whole TDMA frame, and one burst in it is the amount of data that's transmitted during 1 time slot. What are configuration options? Well, time slot 0 is almost always used for beacon or broadcast or signaling channel, whatever we would like to call it. So that's where all the public announcements are made about pagings and about the system about the information about the system. Like, okay, let's say I'm a Vodafone cell tower, and and there are also other Vodafone cell towers around here, and their frequencies are this and that and stuff like that. So there is, excuse me, a lot of signaling data and helping data for mobile equipments to find the best cell tower to connect to. So that's what time slot 0 is for. And time slot 1 to 7 is used for actual data transmission, like voice calls, or if the mobile phone needs to switch on encryption and go to a different time slot to receive like an SMS or stuff like that. And there is a lot of way to organize logical channels, and it's always depending on the carrier and also sometimes on the certain cell. So I would just wanted to give you a whole list of logical channels that's up there. It's a huge list, and as you can see, huge amount of shortenings and three-letter words. So you don't need to know much about this. I just wanted to put it out for you so you can see that there is actually almost a single logical channel for every single function in it. So there is like frequency correction naturally in it, also for synchronization. But also if you would like to have fastly associated, then there is a fast associated control channel. But there is also slow associated control channel if you want to do it just slowly. But also there is a paging channel where all the pagings are going, or there is a random access channel where you can ask for access from the tower. And then there is a different channel for actually granting access. So yeah, it's full with logical channels. So what's the outline of hacking GSM, how to crack the key and how to listen to the conversations? This is the steps that Karsten Knoll showed us also in 2010 and also in 2011. So the first step always is getting into the same cell as the victim number and uncover his or her TIMSI. TIMSI is a temporary mobile subscriber identifier, and it was created so that even if you're listening to the public announcements of the GSM network, you would not be able to figure out like which customer is actually on that specific cell. So instead of using phone numbers, which would be like, based on phone numbers, it would be easy to identify customers. They are using a temporary identifier, which should be changed like by every single transaction. It's not changed by like that. It's changed almost like every 24 hours or so. And the main idea about why we need to get this, because based on the temporary mobile subscriber identifier, we will be able to figure out that, okay, our target is here. So when the target gets paged, we can start sniffing and recording data, because we need to know when to start with sniffing, because there is a lot of data coming through, but we need to be able to distinguish like, okay, this is the time point when we need to start listening, because that specific TIMSI just got paged, so there must be some kind of transaction going on, because every transaction starts with a paging. And then also we need to analyze how the cell is configured. We will talk about what that means. And then we need to capture some data, of course, and based on the analysis, we need to create input for Kraken, which is the cracking tool for GSM. I mean, the cracking tool for GSM, it means that it can crack A51 keys. And after the key is cracked, we can just use it to decrypt the full conversation of what we just have recorded. So getting into the same cells, you can use HLR queries, and I don't want to talk really much about this because this technique is well known since 25C3, so that means like almost for 5 years it's been known. Online, you can just go there, put in the phone number, and you will get some information about the victim number, and that also gives you a rough location. And then if you would like to get closer, we need to actually uncover the TIMSI. So to get closer, we need to do the theory of uncovering the TIMSI, which means how would we be able to actually match a TIMSI with a phone number? Well, we know that every single transaction that specific customer is receiving on the phone is started by a paging. So what if we could just keep giving transactions, or let's say that, giving transactions to that specific customer, to that mobile ID, to that phone number, and look at the pagings and try to correlate with what we have given. So let's say we will give 10 calls to a customer, and we will see that the same TIMSI is being paged 10 times on the air. And that's something, that's a pattern that you can notice and figure out, like, okay, this was the same TIMSI paged over and over again, so that's the victim, that's the phone number I'm looking for. So right now I have a phone number and a TIMSI, and I know that they are together, they are connected. So, naturally, we don't want to call the victim because that wouldn't be quite efficient. He would see that, okay, I had 10 missed calls, that's not nice. So why don't we use silent text messages? Silent text messages are quite funny in GSM. I don't know why they were created, but what they do is that when you send them, the victim needs to acknowledge them, so tell you that, okay, I got that message, but it will not show anything on the screen, nothing will happen, no beeps, nothing. You will just know that, okay, the victim just responded. And naturally, it also starts with the paging. So if I send like 10 silent text messages, then I will see 10 pagings for that specific phone number and figure out, I mean, to the specific TIMSI, and then figure out that, okay, that TIMSI is for that phone, connected with that phone number. So how do we do that in practice? Well, we need to simultaneously monitor the air for paging requests and also send silent messages, and we need to correlate the data together. So the architecture I created has 3 main components: a silent SMS sender, a correlator, and a pagings monitor. So for sending silent SMSs, it's not that easy because I use an Android smartphone for that, because Android has some internal hidden APIs which actually let you modify the raw bits and bytes of an SMS before it's being sent out. So I'm able to actually get the bytes, switch 1 byte in it, that would make it a silent message, and then send it out using these APIs. On other phone platforms and architectures like iOS and stuff like that, there is not much of like APIs available. So I would suggest, if anyone would like to follow that lead, use an Android phone, possibly. You need to get root access naturally to be able to call these internal APIs. For correlating the data, naturally, using a PC is a good answer to that. And what about monitoring the pagings? Well, there are 2 options to that. You can use Osmocom BB, because Osmocom BB has a firmware created by Nico Golda that will actually print out all the TIMSIs that are being paged right now on a specific cell. So that would come quite handy, because we need to just parse those TIMSIs and then correlate it with the silent messages we sent. Or also you can use RTL SDR, but as I said, it sometimes can get quite messy with RTL SDR, because sometimes it just gets out of sync, and then it needs to be recalibrated again. So for this attack, I'm going to use an Osmocom phone. And I'm hoping it's going to work out, because it's quite a busy cell right now here, because so many people are connected to it. I tried it at home and it worked, so I'm really hoping for the best. And here you can see a screenshot of silent SMS. So this is how it looks like. What it does on the Android phone, it starts up a network listener, and the phone is connected via USB networking to my computer. So my phone actually logs in using Telnet to the silent SMS app, and then tells the app, okay, send a silent SMS to this phone number. And then the app will say, okay, I send this SMS, and then some minutes later or some seconds later on most networks, you will get back an answer from the Android phone app saying that, okay, the message was delivered. So yeah, let's try that. So to do that, I'm going to get into my other laptop and start up Osmocom BB. And as you can see, maybe, well, I'm not sure if you can see that. Maybe I can increase the font size a little bit, zoom in. One more time. So what happens there is the long command in the beginning, that's just for loading the Osmocom BB firmware onto the phone. And then as you can see, I piped the output of that command to the TIMSI Buster Python script which I created. And then the Python script is going to parse the output of Osmocom BB. And then since the output contains all the pagings, it will use that data. And also, the TIMSI Buster is capable of telnetting into the phone and telling it to send the text messages. So I will start up the silent SMS app right now, and it's up and running. And here we go. What I need to do is start up the Osmocom BB phone, just a short push, and maybe a shorter push. All right. Osmocom BB can be sometimes tricky, but everything seems to be connected. Okay, how about we stop this and get the battery out, because that's always fixing the problems. Since Osmocom BB always runs in the RAM, you need to clear the RAM sometimes. And the best way to do it is just pulling the battery. Okay, let's wait a little bit. Here we go. So Osmocom is loading up, and we need to just wait a little bit more to have the firmware up and running. And right now the firmware is up and running, and it would like to know like which cell I would like to sync this Osmocom BB device to. So we need to put the Osmocom BB device on the same cell as our victim by telling it the ARFCN, so the frequency of the cell, and then Osmocom BB will sync to that cell and start outputting the beacon channel's content. So I'm using an old BlackBerry because it has a nice network monitoring mode, and it can tell me like which cell it is camping on right now. So it says it's on ARFCN 48. So what I need to do is just press 48 on the phone, enter, and then hitting the green button will actually sync it. And then from now on, it's going to be automatic. And it's sending the silent messages, and you can see all the pagings up there. And SMS 0 just got delivered, so that means the first silent SMS was sent to the phone. So you can see nothing happened on the screen, no beeps, nothing, because it's a silent SMS. This BlackBerry handles it quite well. So, but that's true for all phones I tried so far. So Android phones, iPhones, stuff like that, they all capable of handling silent messages by giving no answer. So it actually gave us back 2 results, and let's check if, well, what you would do as an attacker now is run this again and see if you have a match. Like if you run it again, then it will tell you probably the same TIMZ. But right now, if I just go to this BlackBerry and say mobile identity, and the TIMZ is right here. I'm going to read it for you, 5181D43. As you can see on the bottom, that's the TIMZ which you just found. So here I was able to match the phone number with the TIMZ on this phone. OK, so first step is done. We have the TIMZ. Now let's get back a little bit to the presentations and see how we're gonna crack the GSM. Okay, so what's the theory of cracking GSM? Well, the idea is it's a known plain text attack, which means that in GSM there are many frames or bursts sent out in the air that has known content, and these bursts are sent out periodically, which means that like every third packet or every fourth packet is going to be the same, containing like system information about the cell, like the cell's name or the cell's operator, all the alternative cells that are around and are part of that operator's network. So, and the problem is that even when the phone is communicating with the GSM cell via an encrypted channel, these messages are being sent, naturally encrypted. And the encryption means there is a key stream generated from the session key, and that's XORed with the plain text. So this actually ends up giving us a key stream, so there's key stream leakage. And the key stream is what we need to input to the cracker. So let's go through that one more time so everybody can just get it together. Like, so when you look at the cell, you will see that there are system information messages like every single third time or fourth time, so however. And then if you look at the encrypted data, you could know that, okay, every fourth or every third is going to be a system information, and the content is known from the previous analysis of the cell. So if you just put those two together by XORing them, you will actually end up with having key stream, and this key stream could be inputted to Kraken, and Kraken will give you actually the A51 key. Of course, there are practical problems with that, and the hard part is to determine in the huge encrypted burst, huge amount of encrypted bursts which you can see, like which messages containing known plain text, so which ones are the system information messages. That's why you need to do analysis on the cell before you start to attack a victim, which should be actually yourself. Well, yeah, legal disclaimer. And because there is no way to differentiate between like system information messages and other type of like actual data messages on the air, because every single burst has a fixed length. So like in Wi-Fi, you would be able to identify ARP packets even when they are encrypted, because they have that specific short length, and you can see that without knowing the encryption key. But in case of GSM, you don't know that because everything has the same length. So that's why it's a little bit harder to do, and that's why you need to analyze the cell and figure out like when is a system information message coming in, so you can then figure out in the stream of encrypted data where is that system information message. And then let's talk a little bit about Kraken. release the Kraken. So it's a tool created by Frank A. Stevenson, who could be known for cracking the DVD content scramble system back in 2003, I guess. And what the tool does, it uses 2 terabytes of rainbow tables, which I happen to have here right on my hard disk, to crack GSM. And also, if you'd like to if you'd not like to download the tables, naturally, because you can contact me because I have them here, and I would be happy to copy it to your hard drive anytime. And probably also in the Hackerspace Budapest, there is going to be a copy of it. So whenever you would like, you can just drop by, drop your 2 terabyte hard drive, and we will probably be able to copy it for you. And the good thing about Kraken is that even the cloud could be used to use Kraken, to run Kraken. I tried it on Windows Azure, and mainly because it has quite an easy options to attach 1 terabyte disks to virtual machines. So I actually created a large size virtual machine, attached the 2 terabytes of rainbow tables to it, and I got quite good results. It took around 68 seconds to crack A51 key. And on my computer, it took around 180. So Azure was actually faster than my computer. And I also contacted with Maxim Orlinspike, who is running cloudcracker.com. And he said he is actually talking with his lawyer about this. It might be possible that Cloudcracker is going to offer GSM cracking possibility for you. So you just need to enter these keystream bits into it, and it will actually give you back the key for some dollars. But I cannot tell you this for sure, but I just wanted to say that, yes, we actually started to think about that. OK, so let's get back to our demo here. So what I would like to do now is show you how to capture data, and then how to parse the data, and how to get some 5 minutes left. OK, we need to really speed up. OK. I have this stick here, and using GNU Radio, it's really easy to actually just capture data with it. So what you need to do is, I'm just going to go to, it's actually in GSM, or it's in, no, it's up there. Oh, yeah, it's common SDR. So in GNU Radio, there is actually a different branch for RTL SDR, and then you can use that to capture data. And when you end up with data, you need to convert that, and there is a program for that. It's called GRC, and all these steps, like how to convert it and stuff like that, is actually online on a blog, which I will give a link to, and I also write about it on my own blog. So once you have received these data, then you will have such data files, like a C file, call.c file, for example, or other files here, and that C file needs to be parsed. So how do we parse it? There is a tool for that. It's called go.sh, and then you need to give it some parameters. 64 is always the first number, and then 64 means the decimation rate of the stick. And the second parameter is going to be the time slot, which you would like to look at. So always start with this time slot 0, because that's the beacon channel, so you can see the data. And you need to give it a configuration, which could be like 0C. And then you can give it the key if you have it, but I'm not going to give it the key. I just would like to show you the beginning of a call. Here we go, without the key. And it runs through. And in Wireshark, you can actually follow these packages along. And yeah, I have some DNS from Ubuntu, but as you can see, go a little bit up. Here we have some packets up there, and as you can see, there is quite a pattern here. There is a paging request, there is another paging request, there is system information type 1, and there is paging request, system information type 2, paging request, system information type 3. As I said, there is a lot of data that's being replicated on the air. So, but now I would like to show you Kraken. I'm going to use the Azure server because that's a lot faster, I guess. So let's just enter to the Kraken's directory and cd to the Kraken and start it up by telling it that the index files are loaded up in mount. Where is it? It's in Kraken, and then in indexes. And it will just load up all the tables. And I have already analyzed this data here for this call, and I have XORed one packet out of it. So if I would just go there and, which one is that? Call Kraken. So this is the data which I need to enter to Kraken. This is one burst and just saying it crack. So that's all what it needs. So let's get back to the Kraken. It's loaded up and let's start it. It's going to take around 60 seconds for it to go through that 1.6 terabytes or 2 terabytes of rainbow tables and try to find this specific burst and try to find like which key it could be used for. And the other problem with GSM is that more keys could actually be resulted in the same encrypted text or in the same key stream. So after we were able to figure out after it gives us an output, that's actually an output for a candidate key. So we couldn't be sure that that is the certain key. So there is another tool for that. It's called find KC, and we need to enter the candidate key to it and give it the original burst. And we also need to give it another burst from the same conversation. So it will try to use that candidate key and see if it encrypts the second burst, does it get the same key stream? So using the same key stream, one more minute. Using two different key streams, we can actually verify that if the two key streams use the same key and end up in the same result, then naturally they mean we have the key. So since I already have this command, I'm just going to run it here, and it will give us the key. Here we go, and paste it here. And as you can see here, it says matched. So I'm just going to really fast copy this key and parse the call we have. So it's called call.cfire and 64. And the call was on the first time slot, and the configuration was TE. And removing the spaces out of the key. One more space, actually a lot more spaces. Here we go. And now it's trying to find the data in it. There is a lot of errors in the beginning, but after that it will actually be able to find the correct data in it. There is a lot of junk with a different key, but then there is going to be my call, and I'm just going to play you the call so you can hear it. Yeah, you can see that's actually the data from the call, and as you can see, it was able to parse it, so the key was correct. And once it's done, just some more seconds, we will have it. And yeah. It's just so frustrating when there is no time for you to talk. Okay, it's getting... okay, I will just slow down the process a little bit, so... Okay. Seriously. And the output is called speech.amr, and we need to have, sound. Yeah, we have sound. Hopefully. Okay, VLC is still starting up. It's a command line VLC, but it still takes a lot of time to start up. That's fine. Yeah, I know it's fine. Thank you, man. Okay, I just disconnected my Wi-Fi, but it should be still. Okay, VLC. Here we go. There we go.
Welcome to the Vodafone Passport information line. For information about Vodafone Passport, press 1. Sorry, I didn't catch that. For information about Vodafone Passport, press 1. Or to add Vodafone Passport to your price plan, press 2. Vodafone Passport can be used in Albania, Andorra, Australia, Austria,
I let it to run to Hungary and then stop the call.
Bosnia-Herzegovina, Bulgaria, Canary Islands.
It's a United Kingdom Vodafone SIM card I use, and that Vodafone SIM card had a customer service for people who are outside of the United Kingdom, and I was able to call that from here. It's a free number, so that's why I did it, and that's what you can hear when you do it. So I would like to give many thanks to all these people listed here. I cannot tell all the names because the time is really running out, but these really helped me a lot. And cheers naturally to Camp Zero and Hungarian Hackerspace. There are a lot of links, and all the code, as I said, will be released on GitHub. And also I will post a whole write-up about what just happened here at my blog, probably this night or maybe next night. So the blog is right on the bottom, you can see it. There is no time for Q&A, catch me if you can. Thank you for your attention, that was me.
Ladies and gentlemen, Domonkos Tomcsanyi.